be telling you a little bit about our Quantemol-EC software. So for this, I'm going to be giving you a quick guide to using Quantemol-EC. First, I'm going to be presenting some facts about Quantemol-EC and a little bit of information, and then we're going to go through a quick demonstration of how to use it in order to calculate the vibrational excitation cross-sections for an exemplar molecule water. So as a quick introduction to Quantemol-EC, Quantemol-EC calculates electron molecule scattering cross-sections. It's based on a new suite of R matrix codes, and it interfaces with the quantum chemistry software MolPro, as well as the UKR Mol Plus codes in order to generate accurate cross-sections. So some of you might be familiar with our predecessor software to Quantemol-EC, Quantemol-N, which also calculated electron scattering cross-sections. So I'm going to quickly take you through some things that Quantemol-EC can do that Quantemol-N cannot. So Quantemol-EC allows for the automatic generation of configurations, automatic symmetry detection, and the handling of degenerate states. This means it's a lot easier to use for people who don't have expertise in these specific areas. It makes it a lot more simple, straight out the box. It also provides more accurate ionization cross-section calculations. And finally, it has access, as I just said, to the most recent suite of R matrix codes. So what we're specifically presenting today is Quantemol-EC 1.2. So Quantemol-EC 1.2 is our most recent update upon Quantemol-EC. And I'm just going to tell you quickly about the two major features which have been added. The first major feature which has been added is it gives you the ability to calculate non-resonant vibrational excitations for ions and neutral species, which is actually what we're going to be having a look at quickly today. The second thing which has been added is it can utilize effective core potentials for ionization cross-sections. These are very useful for calculating things with heavier atoms. If you have any interest in Quantemol-EC 1.2, then there are availability for free trials. So if you want a free trial, then feel free to email us at support@quantemol.com or visit our website at quantemol.com and fill out a form for a free trial. And that will give you a 2-week free trial. And if you have any general questions which you don't want to ask in the talk or you think of after the talk, then feel free to email support@quantemol.com for that as well. So I'm quickly going to be taking you through a case study for calculating the cross-sections of the exemplar molecule water. Okay, so just bear with me one moment. You'll have to excuse me if I'm a little bit croaky. I've got a slightly sore throat. But when you load Quantemol-EC, the first thing you will see is this page here. So in order to start a new calculation, one clicks File and then clicks New. So there's two ways of adding your molecule, adding the geometry of your molecule. The first one is to add it manually by adding atoms one at a time. And the second one is to add in an XYZ file, which you might have downloaded from a database such as the NIST database, or you might have produced in another piece of software. So I'm going to first take you through how to add atoms manually. So in order to add atoms manually, one clicks Add Atom. It will bring up this little dialog box. For this, you will say the atomic symbol of the atom. And then I'm going to just quickly put in some coordinates, which I've looked up earlier. So it's some XYZ coordinates for this. So if you don't have the coordinates for your molecule, as I said earlier, the NIST web database is often a very good place to look for it. So I'm just going to quickly add in my oxygen. And then finally, my second hydrogen. And there you have your water molecule. This will have the bond lengths written down here for convenience and the bond angles written down here. You can also edit your coordinates here if you wanted to have another go at it. So obviously, this is a fairly rough estimation of the water molecule. So one thing which QEC is very, very useful for is its MolPro integration. And in this case, you can use a MolPro geometry optimization to get a more accurate geometry. So for this, you click Optimize. This gives you a choice of basis sets. If you have specific knowledge of what basis set you think might be useful for this calculation, then feel free to change that. But if you are not familiar with this, then feel free to use the defaults. They work very well. You also can choose your method. You can either use Hartree-Fock methodology, or you can use density functional theory with the B3-lip functional. Again, if you don't know much about that, then feel free to use Hartree-Fock as a default. It works perfectly well. And then finally, you can suggest what you'd like your charge to be. So whether your molecule is charged or not. So if I click OK on that, as long as it's a reasonably small molecule, which it is, it should go very, very quickly. And then it will give you the option to save your geometry file, so you don't need to re-optimize it, which can be useful if you've got a larger molecule. In this case, I'm going to click no. And then, so that's one way of generating your molecule. Another way of generating your molecule is to do it from an XYZ file, as I said earlier. Now that's really easy to do. You just go File, Open Geometry. It'll ask if you want to clear all the data. I can click yes, because I don't mind about that. And then I can go to a place where I've saved it. So in this case here, click Open, and that will put my molecule in. So this is a fairly crude version of the molecule. So again, I can click Optimize on it, and then click OK. And that will upsize my molecule. Again, I'm not going to save it. A very important thing to do at this stage is to click Center. This puts your molecule into the center of the box. So yeah, that's going to be important for later calculations. So then we're going to click the next button to get onto the next step. So for this bit, this is another key advantage of Quantemol-EC. This is where we do the automatic symmetry calculation. So this will calculate the symmetry of the point group, so you don't need to input it yourself. It'll just do a very quick mol-pro calculation to work out the point group of your molecule, which again just makes the whole thing easier to do, so you don't need to worry about working that out for yourself. So you click OK on that. That'll be very quick as long as your molecule is not massive. And then it will tell you your symmetry down there, which you can check you agree with. And it will show you your planes of symmetry. And on this page, you do your next step, which is to select the orbitals which you wish to use for your calculation. You can either use Hartree-Fock orbitals from a HFSCF calculation or natural orbitals from an MCSCF calculation. So if you don't know which one you might choose, then you can potentially either email us at support@quantemol.com, or you can look at the citation, which I'm going to be sending out to everybody after this workshop. But just as a general rule of thumb, Hartree-Fock is a little bit quicker to use. It takes less time, but MCSCF orbitals are crucial if you're doing electronic excitation calculations. So in this one, we're going to be using Hartree-Fock because I'm not doing electronic excitation calculations, and I'd like a nice quick demonstration for you all. You also can select a basis set of your choice. Again, the default ones are absolutely fine, but if you have any knowledge in it, then you can change that. Also here we have the option to have a look at some advanced options. So some advanced options including the effective core potentials, as I said earlier. If you click on this, then it will give you a list of molecules you'd like to use effective core potentials for. This is good for your heavier atoms. It also gives you the option to input charge, multiplicity, or symmetry at this stage, and also to change your memory requirements. If you're interested in SCF calculations, then also that you have the option here to change your active space. Now, if you don't know what that is, then don't worry about it. But for those who have knowledge of active spaces is basically which electrons and orbitals are involved in your calculation. The default one for a mol-pro calculation is the valence orbitals. However, if you do want to change that, then we would recommend that you try no more than 10 electrons and 10 active orbitals. Otherwise, the calculation starts to get quite slow. But if you have any questions about the active space, or you want to talk to us about anything of this nature, then again, feel free to email us. But yeah, very, very useful to be able to change this if you know you want something, or you want to look for something. But if you don't, then don't worry about it. So next up, we will be clicking next on this. So I'm going to be going back to Hartree-Fock SCF again, because we don't want to be doing the really expensive calculation. And we've got some more things to set up. So on this one, the first thing we're going to be having a look at is your R matrix sphere size. So you want your sphere to be large enough in order to encapsulate your molecule and all of its orbitals, but not so large that the calculation is really expensive. So generally, an R matrix sphere size of 10 is fine, but sometimes if you've got a bigger molecule or you've got especially diffuse orbitals, this might want to get a little bit bigger. If this is the case, then you will normally be given a warning, but often you can talk to us if you think that might be the case for your molecule. So I'm going to be using a default of 10 because water's not too big. Then you have your methods. You can either use, if you're using a Hartree-Fock, you can either use a static exchange method or static exchange with polarization. For the details of these, there's a citation which I'll be sending you afterwards, the same one I just mentioned. If you have chosen MCSCF calculations, then your method will be close coupling. Finally, you can change on this page, you can change your scattering energy grid. If you make this smaller, then your calculation will be quicker, but you will see less generally. But the default one is absolutely fine normally, so no worries there. Again, you have some advanced options. So the advanced options, you can change the total number of states. You can add a vertical excitation energy cutoff, or you can change the number of virtual orbitals or add in extra virtual orbitals. If these things are of interest to you, then great. If not, then don't worry about it. The defaults are probably fine for your situation, as is the case with a lot of these things. So finally, I'm going to click next, and here you can see the list of the different calculations of which we can conduct. So this is the final step, is basically asking what you want for. So there's multiple different things we can do. As standard, we calculate the total elastic cross-section and calculate the eigenphases, which my colleague Harren's going to be talking a little bit about in the next talk. You can also, if you selected the MCSCF route, have calculated the excited state cross sections. That's the electronic excited state cross sections. But as we're doing Hartree-Fock, that's grayed out because we don't recommend those. But if you've done MCSCF, then you could be calculating those. You can also calculate the ionization cross section using the binary encounter of Bethe. If you choose that, then you have some options. So your option is basically, do you want to be using Koopman's ionization level from Koopman's theorem, or do you have a experimental ionization energy which you'd like to input either from one of your experiments or that you found in a database? The default works fine for most cases, but sometimes the an experimental one can make a slightly more accurate result. So that's an option which you can add in if you're interested in doing so or have the means to do so. Or often you won't, obviously. You can also calculate differential, momentum transfer, and rotational cross sections. For these, the things you can do is you can modify your energy grid to make the calculation a little bit faster again, or you can put in calculated dipole moments, which is what you'd use by standard. Or if you have them available, you can use experimental dipole moments. So that's another option if you have that to hand. So those are your general options for that one. So then we have the vibrational excitation cross sections, which is what we're interested in this one. So the options for that is you can change your energy grid if you want it to go a little bit faster. Your energy grid is quite small because this calculation is a little bit more time consuming. And you also can calculate your an estimate of your dissociative attachment cross section. Now, if you're estimating your dissociative attachment cross section, you must include dissociation energy. It needs that in order to calculate the estimate. You can look this up online on many databases, and if you'd like to discuss further with us as to how you might be able to acquire this for your specific system, then we're always happy to have a conversation about that if you email us. But you also have some optional extras for this one. So you can optionally change your vibrational frequencies. So you can either use the default or you can specify your own vibrational frequency. And you can also suggest some fragments that you think might form and electron affinity for those fragments. So those are all things you can add in if you wanted to. So we're not going to be doing that calculation today. And then finally, if you've done the MCSCF calculation, then you'd have the option to calculate inelastic electronic cross sections. So if you were to do that, then it would give you similar options to if you were to do the ionization cross section as to how you want to define your ionization level, either through Koopman's theory or through an experimental route. So when you've done that, then we've selected the ones we want to look at. So when it's all done, we're going to click run, and you will end up with this on your screen. So this should only take, in theory, probably a couple of minutes. So it shouldn't take too long. So just in this time, I'm just going to quickly reiterate that the big benefit of Quantemol-EC, or one of the big benefits of Quantemol-EC, is that your molecules, it's very easy to use. It's very quick to use. It gives you the options to add in some quite advanced stuff. So it gives you the options to change your basis sets, change your active spaces if you're interested in doing so. But you are not obligated to do so because the defaults work really, really well. So it cuts quite a nice mixture between quite advanced science and also quite easy to use science, which is very beneficial for a lot of people, I think. We also have the other great resource for Quantemol-EC, which is that we have some really good scientists working on it, including Harren, who you're going to be talking to, who's going to be talking to you next up. And Harren's always happy to answer your questions and give his expertise as to how you could better run your calculations. So that's always a massive benefit for the software. Further to that, you also have the big benefit of the fact that it's very easy to view the outputs. I'm going to be showing you the outputs in a moment, and they're very straightforward to look at. And this calculation log is very, very useful for when you might have any faults and you might want to go through with Harren exactly how to fix them. So this gives us some good information. So might not seem very easy to read for you, but it can be very useful for us for troubleshooting and the like. So when the calculation is done, then you get your calculation results, which look like this. So this has the results for all the cross sections of which you selected. So for each one of these, you can, so for say total elastic cross section, you can click view and this will give it to you. You can plot your cross section both both linearly and logarithmically in both the X and Y axis. And when you're happy with this, you can click the save function here, and that will save this as a PNG file, as an image. However, if you want to save it as a data sheet, then as a CSV, then I can show you how to do that in a moment. You can also click on view rates, and this shows your rate as a function of temperature, and also includes Arrhenius fitting parameters, which is very helpful. And again, can be plotted linearly and logarithmically, and again, can be saved as a PNG, as an image file by clicking save. You can view your eigenphases, which again, we're going to be hearing a little bit from Harren about later. And again, linearly and logarithmically on the X and Y axes, and again, can be saved as a PNG. So all of them have this functionality of the different linear and logarithmic axes, and also the ability to save as PNGs. You have your ionization cross sections, same again. You've got your cross section here, and you can also have a look at the rates. With our, again, the Arrhenius fitting parameters are available on that one, and again, saving and changing the linear and logarithmic. This is the one which we've calculated. This is our new feature, which is the vibrational excitation cross sections. And you can see these, and you can see some very nice offsets there. So it's nice and accurate, and has its linear and logarithmic, and can be saved as a PNG. Again, rates are available, and with your Arrhenius fitting parameters, all the same. If you were to do other cross sections, then you'd see similar things. And then finally, we're going to have a quick look at the data sheet. So the data sheet gives you some key information on the molecule itself and on the calculation, including its coordinates and its point group and some electronic configurations. It gives you some information on the orbitals and some various information about what you've done. And then it gives you access to your cross sections. So for each of these, you can view the raw data for both the cross section itself and also for the rate data. And if you click save on these, that will save it as numerical data rather than as an image, which is very, very useful, obviously. And finally, we have a reference at the bottom, which obviously you will put in if you cite it. This is a nicely well-cited piece of software. So at the top, we have a link to our Quantemol-DB database, which is a database of different features, which you can have a look at. We're going to be hearing a little bit more about that from my colleague Sebastian and the talk after next. But this is really good for comparing the results of which you've just acquired to. So when you're done with that, you can close this. And then to save this, you export your results directory. So we will put this in here and just save that there. And that saves that directory. And then if you want to view that in the future, then you can click File, Open, Results, and then access it again. Wherever it is, there it is. And if you click on that, then this will pop up again. So that's all very, very useful. So that's how you use QEC to do a calculation of that nature. So as I said previously, If you so there's the citation, but don't feel free like you have to write it down now. I will send it to you afterwards. If you have any questions whatsoever or any interest in a free trial, or you just want to talk to us, then feel free to email support@quantemol.com. Thanks very much for listening, and does anyone have any questions?